네, 다음 강의는 저희 퀀델라의 닥터 라와드 메저님이 해주실 거고요. 강의 주제는 벤치마킹, 포토닉 서킷이랑 그 comparing with other quantum processor에 대한 강의를 진행해 주시겠습니다. 그러면 이어서 이제 두 번째 강의도 바로 이어서 진행하도록 하겠습니다. 예, 감사합니다. 네, Dr. Rawad, you can share your slide and you can take it over from here.
Yes, perfect. Thank you. So just let me know if you see my screen actually
Yeah,
now, or
I can see your screen.
okay. So just to check, can you see my cursor as well?
Yes, it's well written in
Okay,
English. Sure.
perfect. Okay, thank you.
Thank you.
All right. So thank you for the introduction, and I'm happy to be here to present some stuff about what we've been doing in Quandela in benchmarking our quantum technologies. So just a small word about me. So I have a PhD in quantum computing. I obtained it from the Sorbonne University in 2019. I worked as a research associate at the University of Edinburgh in the UK from 2019 to 2021, and then I joined Quandela from 2021, basically. So today, what I'd like to talk about basically is benchmarking. So you saw with Professor Senela a bit ago, somehow the physics part of the quantum computing. Now I'm really going to talk more about the quantum computing side of things, and in particular about how to benchmark the quantum devices, so how to assess their quality. And in this sense, I'm going to try to present more or less like as much of a broad overview of the topics as I can, given the time. And so to start, I'm going to talk about benchmarking generic performance, which is basically random instances of unstructured circuits and how you can benchmark them. And I'm going to talk about two things. So one of these benchmarks is well known and is tailored to the circuit model. It's called quantum volume. So it's the benchmark that IBM and others use to scale up their devices. And another one is the one which we developed at Quandela, which is actually tailored to photonic benchmarking, which is called the PQF, or the photonic quality factor. And more or less, it comes with similar guarantees to the quantum volume, but it's more tailored to that technology. So I'm going to talk then about application-centric benchmarking, which is basically benchmarking specific structured circuits, because so generic is unstructured and they tell you something about somehow the average performance, but application-centric can tell you about the specific performance of the circuit you're interested in doing. And then I'm going to move from circuits to quantum gates. So I'm going to talk about how to benchmark specific quantum gates, which are the components of the quantum circuits. And I'm going to talk mainly about two things. So randomized benchmarking and direct average fidelity computation. And as I hope to show that each of these is suited for like specific hardware, basically. I'm going to talk a bit also about some other kind of like interesting thing is that so people are usually looking at ways to go from the like photonic model to the circuit model. So for example, you saw, I guess in the previous talks, the KLM computing, the Nil-Laflamme-Milburn, where you encode your photons in spatial encoding, and then somehow you perform a computation, and you transform a photonic circuit into a gate-based circuit. Here, I actually want to talk about the inverse. So how do you transform a gate-based circuit somehow into a photonic circuit? So there are both ways somehow. So this is what I plan to talk about. Okay, so I start a bit with the motivation. So why is it interesting to kind of pursue quantum computing? And I guess most of you are familiar with the catch, basically. So quantum computers promise some really interesting tasks. So they promise that they can factor integers in polynomial time. So basically, they can crack common encryption schemes. You can search through unstructured databases through Grover search, quadratically better than the best classical algorithms. And this is also like a huge improvement for various applications. And also you can solve some other tasks polynomially faster, for example, machine learning and so on and so forth. So there's really, of course, among the others, like quantum simulation and quantum chemistry and all those other nice applications. But of course, there's a catch. And it's that quantum computers have to be fault tolerant. And so what does it mean for a quantum computer to be fault tolerant? So basically, to be fault tolerant means that you should be able to perform error correction on your device. And one of the very common and most explored ways to perform error correction is through the use of what's called the quantum error correction code. So essentially, the quantum error correction code is a way to encode information in a redundant way. So you have a bunch of qubits, and you entangle them in a larger quantum state, and this entangles a quantum state you call your logical qubit. So one logical qubit is a bunch of physical qubits, such that if you lose information about, on a few of these physical qubits, you can still recover the information from the logical sense. So from the entire entangled state, and this of course depends on the rate of how good your individual qubits forming the logical qubits are. So you need very good physical qubits to begin with, because there's what's called the fault tolerance threshold. And this quantum error correcting codes are usually tailored to perform a specific set of gates, which are called Clifford gates, which are not enough to perform universal quantum computation. So you need to add on top of it a sort of distillation procedure to purify magic states or T states, which give you the universality. And this magic state distillation is also something which is costly in its own sense. So just to avoid the jargon, a magic state is a state which looks like this. So it's a pi/4 rotation. And if you add a magic state on top of Clifford operations, which are basically a Hadamard, a C0, and a phase gate, then you get universal quantum computation. So Hadamard, C0, and phase gate, some very common error correcting codes can do fault tolerantly, but can't do this T-state fault tolerantly, so you need a distillation procedure. And combining these together gives you fault tolerance. But we're not there yet, basically. So we have some very promising proposals, but the number of qubits or the number of photons required to reach to reach the capabilities of performing good error correcting codes is very high, basically. But you still have some very promising paths to pursue, and mainly in photonics and mainly in measurement-based quantum computation, as you just saw with Pascal a few moments ago. So there, the key idea is to create highly entangled states through fusing small resource states together, basically. So resource states are the states you can generate, say, for example, from your source, and then you fuse these together, but they're small. Somehow they're small photonic states, and you fuse them together. So you kind of paste them together to create a bigger entangled state, and then you use this entangled state in a specific way to perform fault-tolerant computations, which is called measurement-based computation. So, but as I said, so we haven't reached that point, and actually it's not the main focus of my presentation today. So actually the main focus of my presentation today are the devices we currently have right now. And these devices, they're usually called NISQ, or like noisy intermediate scale quantum devices. And you have really two versions of NISQ devices, more or less. So one of them is very common and is very well known. It's the circuit model, which is basically a bunch of single qubit and 2 qubit gates, C0, Hadamard, T, which we saw earlier, and so on. And another one is the photonic NISQ device, which is what we have actually at Quandela, which is basically composed of 3 components. So you have single photons coming from the single photon source. You have a universal interferometer, which can implement any M-mode unitary transformation. And you have a bunch of detectors which detect the outcome. And you can go from one, so from, for example, the photonic picture to the circuit picture using the KLM encoding, which I guess you saw in previous talks, so Mill, Laflamme, Milburn. And the inverse, actually, which I'm going to talk about a little later, you can even go from the circuit to the photonic picture using what's called the boson sampling encoding, which I want to explain later on in this presentation. And just to say, so these are the 2 types of devices which are currently available. They operate on a relatively small number of photons and qubits, so qubits in the matter-based and circuit-based, and photons in the photonic-based, and they actually have very different noise sources. So like, for example, if I'm looking at the circuit picture and superconducting hardware, the main sources of noise are so you have a lot of Pauli stochastic noise, you have a lot of measurement noise, you have a lot of time drift effects, decoherence, And for us, when you're looking at photonic processors, the main sources of noise are photon loss, or distinguishability of the photons. So like when the HOM is not perfect because the photons are not interfering very well, and so on. So different noise sources, which kind of implies we need more or less different benchmarks. And this is what I would like to say. But before going on to benchmarking, I would like to motivate why it's, even if we don't have fault-tolerant quantum computers yet, it's still interesting to explore what these NISQ devices can do. And this is exactly what we are doing. And so the first motivation is basically you have a lot of experiments which are coming out, which are claiming quantum advantage these days. And so the quantum advantage they're claiming is basically very specific. So it's for a sampling task. So it's a mathematical task. And the goal is they create a big enough quantum system, and they perform some sort of random circuit on this quantum system, and they look at the output distribution. And the claim is that you cannot sample efficiently from this output distribution with a classical device. So the quantum device, which is this big quantum system and some random unitary and some measurements, is performing a task which is sampling, which is not performable efficiently on a classical device. So these are the basic claims. So some of the two most popular are the matter-based, which is the Google Sycamore experiment for quantum advantage, and the other one is in the group in China, which is the Gaussian boson sampling, basically. So these are very interesting. Of course, people are trying to challenge these experiments by actually showing that, well, because of the levels of noise present in these devices, you actually do have efficient classical algorithms which can perform the tasks they claim these experiments claim to perform. And a lot of times people are successful in finding these efficient classical algorithms. But the point is that we will reach a size where these classical algorithms won't work anymore. And really, this is the interesting and hopefully what we will achieve in the near future. The second thing to convince about using NISQ is that actually it might be even useful for quantum advantage, basically, and useful quantum advantage. So what I explained earlier was a type of quantum advantage sampling, which is a mathematical task, which is not necessarily useful. But actually what we're discovering is that it might be useful for specific tasks, like, for example, in machine learning, this article, which claims a provable advantage in learning from experiments. And also here, this paper of the evidence of the utility before fault tolerance also explores a set of circuits which might actually perform something useful and give you a quantum advantage. So it's not clear that we need to wait for a full fault-tolerant quantum computer to be able to do a useful algorithm with an advantage. And of course, NISQ devices are the natural intermediate step between nothing and the fault-tolerant computer. So it's worth studying them. It's worth understanding the different noise models to be able to create better error correction codes in the future. So this is the motivation. So what I'm going to really talk about today is benchmarking these NISQ devices. So it's very important to benchmark these devices to understand their quality. And there's a lot. So there's a zoo of benchmarking protocols. So if you see this figure here to my right, so you have a bunch of names like tomography, randomized benchmarking, blind verified computing, so on and so forth. And each of them come with their own assumptions on the noise, on the security of your scheme, and each of them come with their own information gain. So for example, in tomography, you're really reconstructing the entire state, so you're gaining a lot of information. Whereas in randomized benchmarking, you're taking one number out of the state, which is the average fidelity, which is not a lot of information. But also there's a trade-off, because the more information you want, the more non-scalable your benchmarking technique is. So for example, to perform full tomography, you really need a number of measurements, which is exponential in the system size, so it's not computationally efficient. So there's really a trade-off between how much information you would like and how scalable your techniques are. So what we will focus on is a subset of these techniques, which are being implemented on NISQ devices, basically. So the first one, which I want to talk about in details, is the quantum volume benchmark. So the quantum volume benchmark assesses generic performance, basically. So it's looking at an unstructured circuit, a random circuit, and we would like to know, on average, how good this random circuit is at producing the outputs. So if there was no noise, then the random circuit would be perfect. But the point of the benchmarking is to assess the quality of the random circuit in the presence of noise, basically. So this is the setup here. Oh, sorry. So this is the setup. So the random circuit is a bunch of 2-qubit gates, basically, and these 2-qubit gates are chosen from the Haar measure on SU4. So the Haar measure is just a technical term for choosing a gate at random uniformly from the unitary group. The pi is a permutation, so it allows you to give all-to-all connectivity. So these SU4 gates are not necessarily acting only on nearest neighbors, but you're allowing them to act on geometrically non-local connectivity. And you're interested in a depth D circuit of this form. And there are results by Aronson and Chen, which study a specific problem on this circuit, which is called the heavy output generation. So given as input a random circuit, the goal is to generate bit strings, a set of bit strings, such that 2/3 of these bit strings have a probability which is greater than the median probability of the distribution. So it's a very mathematical task, basically. So you need somehow 2/3 of your probabilities to be higher than the median probability. But the interesting thing is that this type of sampling problem, or this property of a circuit, cannot be performed on an efficient classical computer. So there is no polynomial circuit which actually has this property asymptotically with very strong evidence, basically. So it's complexity theory, so it's not necessarily a very watertight proof, but it's very strong evidence. And so the idea of the quantum volume is to test if this property is or is not satisfied, because if it is satisfied, then even in the presence of noise, your device is doing something which is quantum, which is non-classical, because no efficient classical circuit can actually do what this quantum device is doing. So indeed, so the idea is, well, basically we want to test for this heavy output generation. So the algorithm is as follows. So I define my individual output as, so if this entire implementation is a unitary U, then my output is something like XU O squared. And my heavy, my set of heavy outputs is my set of bit strings, such that the probability of the bit string is greater than the median. So I compute this classically. So I compute the ideal unitary, and I compute its heavy output set classically. So even if it takes exponential time, but this is what I do. So I brute force compute it classically, and then I run my noisy quantum device with my compiled unitary, and I test how many of my samples are actually heavy output generated. And if for a fixed depth D and over an average of many unitaries, I get that it is heavy output distributed, I keep on increasing the depth D, and I keep on increasing the number of inputs. And quantum volume is more or less the largest input size and the largest depth for which the heavy output generation holds. Basically. So if I reach a point, a certain depth, where this property of heavy output is no longer verified, then the first point at which it's no longer verified is the quantum volume, basically. So I will stop here just to see if there's any questions before I move on.
혹시 여기까지 질문 있으신 분들은 편하게 채팅방이나 마이크 켜고 질문 부탁드립니다. I think, Dr. Mezherga, I think you can just keep going on.
Okay.
Yeah.
No problem. So okay, so this is the test, and so as I said, so the quantum volume is somehow. So first of all, it's a task defined for quantum circuits, and so it's not very natural for photonic circuits. And the reason is because these generic circuits are different than boson sampling circuits, which are the circuits which are the circuits, the photons, which are basically generic instances of photonic circuits. So you can even provably show that the output distributions of the random quantum circuits for qubits are different than the boson sampling distribution. And of course, the encoding of KLM, so to transform the quantum, so the photonic quantum circuit onto a random qubit circuit is costly. So you saw, for example, that implementing an entangling gate is probabilistic and so on. So you need a lot of resources to do that. And it's also not tailored to the noise sources affecting the NISQ devices. So for example, in the matter-based qubit picture, there's no notion of photon loss, for example, or no notion of distinguishability. So we really need benchmarks which target this. And this is the point of this metric, which is tailored to the photonic platform, which is called the PQF, or the photonic quality factor. And so the idea is similar to quantum volume. We're looking at a random circuit in the photonic picture. And the random circuit in the photonic picture is a boson sampler, basically. So it's a set of input single photons, and it's a hard random M mode transformation, and it's a set of M detectors, basically. And you saw that the probability to get an output S given a specific input configuration is proportional to the permanent of a matrix. So the permanent of a submatrix here, basically. So this is the model that we want to look at. And so the ideal distribution is something like the set of all these probabilities, and the noisy distribution is of course affected by noise. And the noise sources which are very common are the photon loss. So when actually some photons are lost, when the photons are distinguishable, and when you have multi-photon emissions, so like your source is not producing a single photon, but 2 photons or more, basically. And here I have a picture of of data actually from Quandela's QPU. So this curve here with the percentages is basically the transmission. So it's 1 minus the loss, basically. So here you see that the different modes are very lossy because, for example, you have a 6% transmission from the output of the circuit. And these graphs here are the HOM curves between 2 by 2, so between 2 by 2 modes, basically. And you saw, for example, that the HOM for our case is quite high, so it's near 100%. So you see that all the modes are more or less fluctuating between 75 and 100%. So this is the distinguishability error, how you characterize it at the hardware level. And this is the photon loss level, how you characterize it at the hardware level. But we're actually interested in quantum information benchmarks, basically. So not in these hardware level benchmarks, which is why we need to develop this photonic quality factor. And so inspired from the experiments, we construct a theoretical noise model, basically. So we assume that loss is uniform. So every mode, a photon is lost with probability lambda, and which kind of more or less looks like this, because more or less all of these are of the same order. And we assume that all the photons are equally distinguishable. And so we model distinguishability by the overlap of the wave function of 2 photons. So if it's 1, then they're perfectly indistinguishable. And if it's 0, then they're not, basically. And so these assumptions have been widely used in previous works. And the idea is really to perform 2 types of tests. So one of the tests is tailored to compute the loss, basically. And the other test is tailored to compute the distinguishability. So in the loss, it's very easy. So you know that the loss follows a binomial distribution. So you just look at the statistics and you deduce the value of lambda. And the test is, you test whether lambda, averaged over many unitaries, is a decreasing function of the system size, basically. So it should be a decreasing function of the system size, or even it should be. So it doesn't necessarily need to be a decreasing function, but it should be less than some decreasing function. So it can be increasing if the other one is decreasing, basically, but it should always be less than some decreasing function. So for distinguishability, we have 2 types of tests, basically. So one of these tests, they target low-order distinguishability, and another type of test, they target high-order distinguishability. So distinguishability has 2 effects, basically. It can affect small, like distributions of a small number of photons, and it can affect distributions of a large number of photons. And the point of these tests is to target both, basically. So, okay, for the low order one, we of course compute low order marginals, so expectation values of occupancies in two modes minus the individual expectation values multiplied. And we compute their moments. So first, second, and third moment. NM is related to first, CV is second, and S is third. And the TD4, we compute a high order marginal, basically, to target the high order distinguishability. And it's the probability that all my photons bunch in the first K modes. And that's it. And the tests are whether these are below some specific decreasing functions of the system size. And so the protocol is very easy from the experimental point of view. You configure a hard random unitary, which is something we can do because our chips are reconfigurable. You set a mode number. So here I set it to 2 plus gamma just to target the efficient classical simulations which exist in this regime, but you can set it really to anything. The tests work for any value of n. You repeat for different hard random u, and then you perform these tests. So the tests, these T loss and the distinguishability test, they rely on collecting statistics, right? So this is a statistic and this is the statistic. So you collect the statistics and you do it, and you do the test. And if all the tests pass, you increase the number of modes and you repeat. So the PQF, like the quantum volume, is the largest number of inputs such that you're still passing the tests, basically. And why it's interesting is that although you don't have guarantees like the heavy output generation, which you know from complexity theory cannot be efficiently classically computed, we nevertheless managed to find guarantees for various classical algorithms which exist. So many of the known classical algorithms which exist for efficiently simulating boson sampling will fail the test after some point. So that's the idea, basically. Okay, and so I can just say that we've computed this benchmark on our QPU, and it has a PQF of 3. So basically 3 photons you can do reliably with passing. So you can pass 3 photons through the 12 modes, and you would reliably pass all the tests which we did. And so just here to like give you an overview of like where the quantum volume and where the PQF sit. So when looking at these benchmarks, basically, you have 4 basic pillars. So whether they give you guarantees. So for example, an example of the guarantee is that no efficient classical algorithm can spoof it, for example, in the heavy output generation, or a guarantee like this, where like we benchmark against the existing and we show that you can't do it. They assess genetic performance, so they're unstructured circuits, they're random circuits, or they're application-centric, so they're structured circuits. And another one which is interesting is that they're hardware agnostic, so they can be applied on all hardware. So the interesting thing about quantum volume is that it comes with guarantees, it assesses the genetic performance, and it's hardware agnostic, but it's not application-centric because the circuit is random, basically. So the PQF, as it is right now, gives you guarantees and assesses genetic performance, but it's tailored to photonics. So it's not hardware agnostic, but I think we can make it hardware agnostic by using some results, and I won't comment more about this. And also, but there's an important factor is the scalability. So the quantum volume is non-scalable because you need to classically compute the heavy set, which involves really beforehand doing an ideal quantum computation on a classical device, which is costly. For the PQF, you just need to collect statistics. So you know what the expectation values are analytically, so you just need to collect statistics, so it's scalable, which is interesting. So now I'm going to go on to another type of benchmark, which is not a genetic benchmark. So genetic, as I said, you use random circuits and you're assessing the performance on average. But these don't necessarily, so if you have a good average performance, it doesn't necessarily mean that for a structured circuit, you have a good performance, so for a specific circuit. And so now the focus is on some application-centric benchmark. the main goal is that you focus on a specific application and you want to know how this noisy device performs this application. So one example is what's called the Atos Q-score. And the idea is you're solving max cut using a specific quantum algorithm, which I'll explain, the QAOA, on a quantum device. So this is the idea of the Q-score. And so I'll go into detail about what I mean now. So max cut is a specific problem, which is why the benchmark is application-centric, because it's focused on a specific application. So what is max cut? So first of all, I begin by defining a graph. So the graph has n vertices and m edges. And the goal is to find a partitioning of the graph, so a division of the vertices into two subsets of vertices, such that the number of and if I do that, then I define the induced subgraph, which are the things in black here. So this is an induced subgraph, and this is an induced subgraph. And all the edges outside the induced subgraph, so these red edges, are what's called the cut. And the goal of max cut is to find a partitioning, so a set of black points, such that the number of red edges is maximum. So this is basically max cut. So the number of edges which are outside the induced subgraph should be maximum. And you can phrase it, the interesting thing is that you can phrase it as some sort of optimization problem. So you optimize this specific edge function here. So Z represents a specific partitioning, and sum from alpha is equal to 1 to m of C alpha Z is a sum of these is a sum of these quantities C alpha Z, where the C alpha Z is equal to 1 if the edge alpha is a red edge, and it's equal to 0 if the edge alpha is a black edge, basically. So we know in the worst case that this problem is very hard, so it's NP complete. And so the best hope is that a quantum device can find an approximation, because a quantum device cannot solve efficiently an NP complete problem. And so one such approximation was developed by Faria and Goldstone, and it's called the QAOA, so the Quantum Approximate Optimization Algorithm. And so what's the idea? The idea is you start with a uniform superposition of bit strings, and each bit string represents a specific partitioning. So you note that the total number of possible partitioning is 2 to the power n, which is why you have like a superposition of n bit strings, because the total number is 2 to the power n. And then you transform this CZ into an operator, a Z operator, and you apply this unitary here with a tunable, which is basically the exponential of this alpha, with a tunable parameter which is gamma. And in order to like induce denseness inside the unitary group, so to be able to explore as much unitaries as possible, you add another unitary operator, which is this B, which is the sum of x's. So Z and X give you some sort of universal exploration of the unitary group, and also beta is a control parameter. And this is really the QAOA algorithm. So you apply this UC with a given gamma 1, and then after it you apply this UB with a given beta 1, and this is a depth 1 QAOA. And you can apply it P times, and it would be called the depth P QAOA, and you're allowed at each P to vary beta and gamma, basically. And your goal, of course, is to find the expectation value of C, right? And the goal is to maximize it, because the solution, if you remember, is a maximization problem. And so you can do this maximization by a sort of variational quantum algorithm approach. So you compute the expectation value, you use a classical solver and or like a classical cost function, and depending on this, you go further. You tune your parameters gamma and beta in the next run, and so on and so forth, until you converge to the solution. And so the interesting thing is that they showed that if you allow your number of layers to be infinite, then you solve the max cut, basically. So this means that a quantum device with the infinite depth can solve max cut. So this is not very surprising, because a quantum device with infinite depth is not an efficient quantum device. So yeah, probably it can solve NP complete problems. So the idea behind the Q-score is basically this algorithm, but for a fixed P, and we solve QAOA for max cut on a graph with n vertices, which is random. So they use random graphs, and whose average number of solutions is known, because so this is important because they compare the performance to the average number of solutions. So an ideal quantum device they compute can solve this problem with a given A% on average. And then you choose an accuracy B%, which is just less than A%, and you define the Q score. And the Q score is the largest N for which you can solve max cut with an accuracy B%. And so it's normal to define the accuracy B to be less than the accuracy of the noiseless ideal device, because we know that a device with noise is less accurate. So basically, so it's a step in the right direction, but as you see, it's still incomplete because it comes with no guarantees. So, okay, what dictates the choice of this beta is not clear. But it's still like a good step in the right direction for this application-centric benchmarking, but no guarantees. So we did some simulations on Percival, which I guess is the software you're familiar with now from the previous lessons. And basically, we tried random graphs of 7 vertices, and we solved using a algorithm which is similar to QAOA. We solved max cut with 96%. But so far, this is only ideal simulation. So we hope to implement it on our QPU in the future and actually compute the Q score, basically. So this is about application-centric benchmark. And so far, what I've been talking about are circuit-level benchmarks, so benchmarks which apply to an entire quantum circuit. Now, what I'm interested in talking about is more specific gate level benchmarks, so benchmarks of quantum gates. So one very common technique to perform benchmarking is what's called randomized benchmarking. And the figure of merit is this average fidelity, basically. So what is an average fidelity? So you have a noisy, so you implement your quantum gate, but actually it's implemented as a noisy channel, which is lambda. So it's not an ideal unitary, but actually a quantum channel, which is lambda. And the average fidelity is essentially I implement my noisy process, and on average, how much of my ideal process is left inside my noisy process. So this lambda psi is my noisy implementation, and the psi is my ideal implementation. And I compute the overlap between my ideal and my noisy on average. And so, of course, if there's no noise, then on average, this is 1, because the overlap between a state and itself is 1. But if there is noise, then it's a quantity which is less than 1. And the way they estimate it in the literature is what's called randomized benchmarking. So they use large sequences of qubit gates, and then they evaluate some sort of exponential function, and from the parameters of this exponential function, they deduce this quantity, which is the average fidelity. And the reason they do this is to isolate the average fidelity of the gate from the preparation and the measurement errors. Because what we would really like in randomized benchmarking is the gate, it's like the fidelity of the gate itself, and not of the faulty preparation and the faulty measurement combined with the gate. But so this is not very useful for our case, and it's simply because, first of all, you need a lot of gates, and as you saw with the KLM scheme, this is very costly. So you need large sequences of gates. And second of all, it's because our measurement and preparation are anyway not that large. So the measurement errors are basically given by the distinguishability, which is very high in our case, and the measurement errors are given by the detector efficiencies, which are also very good quality detectors. So we don't care too much about isolating isolating measurement and preparation from the thing. So which is why we don't do a randomized benchmarking, but we do what's actually called a direct average fidelity computation. So instead of doing this like sequence, this exponential function and so on, we look directly at this quantity and we expand it. So we take our basis of choice, we expand the size in this basis, and we notice that the coefficients of this expansion are proportional to some projector, some well-known projector in math. And then we can deduce these coefficients, basically. And what we get in general when we do that is a very complicated expression for the F average, which depends on the type of unitary you have, but which for very specific gates reduces to very nice expressions. So for example, if we take the famous T gate, which is this pi by 4 rotation, as I said, then your average fidelity is just a sum of 4 probabilities, which are very easy to compute. So P00 means prepare 0, apply your unitary, and measure 0. So in the computational basis, 0. P11 means the same thing. P plus means prepare your state in the plus, apply the unitary, and measure in the plus, basically, basis, and so on. And so it's a very nice way to compute your fidelity. And the interesting thing is you only need one gate. So you don't need a sequence of these. And it works for any gates. So this is kind of the difference. So we did actually implement this on the QPU, and I'm going to show you some results. So we found that, for example, a T gate has a very high fidelity, average, so it's 99.6%. The C naught is around 94%, and the Toffoli is around 86%. And as I said, so these are actually lower bounds because there is a bit of preparation and measurement, so these can actually be better than what's reported. And so, but you see, like in comparison to like other platforms, for example, superconducting, you have really like a difference between, for example, a T gate in our case and the T gate in their case. And the reason is it's because this benchmark is really not tailored to their hardware, because their hardware has huge measurement errors. And so these measurement errors are taken into consideration by our technique. And so really, in their case, it's more interesting to do a randomized benchmarking to get a more accurate estimation. So this is really what I want to convey, is that to do a good and fair benchmarking of your hardware, you really need to know the details of your hardware and what's your strong suits and what's your weak points, basically. So it's very important. So okay, I just wanted to present finally some stuff also we did. So if you remember, I was always talking in this entire presentation about things which are doable in the circuit picture are not natural for photonics because of KLM and because of the probabilistic entangling gates, so you get an overhead. But what I would like to say is that, and which is not very much highlighted in the literature, because most of the literature is focused on other types of technology, is that actually there are tasks which are natural for photonics, but which are not very natural for quantum circuits. And one of these tasks is boson sampling. So for example, to simulate a boson sampler with n photons and m modes, we need this many qubits, so m log n order qubits, and we need a bunch of n squared by n squared unitaries. So each Mach-Zehnder in your interferometer can be modeled by an n squared by n squared qubit unitary, and you need this many qubits. So already this is a lot of qubits to simulate a few photons, basically. So there are, of course, more economical translations than this kind of naive one, but still we expect them to be more or less very, very like similar and not very natural. And so, okay, just to give you an example of why this is interesting. So you saw the HOM effect earlier. So the input is one photon in each mode. The output, so the circuit is just a 50-50 beam splitter, and the output is one of two, like either two go here or two go here. So these are the two possible outputs. So when you want to simulate this as a quantum circuit, this is what it looks like. So it takes 4 qubits. It takes a 4-qubit unitary, which is decomposable using the transpiler for Qiskit as 800 gates. So you need 800 gates just to simulate this one, and 127 of them are 2-qubit gates. So already it's like extremely costly to do this. And what's interesting is that, so I told you that, well, there's only 2 possibilities in the HOM, but here we actually get 16, and it's because of the noise. So the noise is giving you an output which is totally uncorrelated with the ideal output. So if the output was ideal, then you would need just to observe two peaks. But actually look at how much peaks we observe, and more or less, so this is more or less white noise. So this is kind of just to highlight that the other way around is also true. Okay, before I end, I just want to say a few words about this about a nice potential platform which might be interesting to some of you. So it's called Metric, and it's basically a platform where people share and test benchmarks. So, for example, many of the benchmarks I talked about here are already found on Metric, and people have tested them. So, for example, this is a test for quantum volume for different in different number of years, submitted by different companies on different quantum hardware. So it's really interesting, and it's really interactive because the community is using it basically. And so there are many quantum information benchmarks like the ones I've been talking about in this talk, but there are also many hardware benchmarks like coherence time, HOM, photon loss. So there's a distinction, as I said, between benchmarks which are relevant for quantum information and benchmarks which are relevant for the hardware. And really both these benchmarks are found there, basically. So I'd just like to summarize. So you have many types of benchmarks for the quantum hardwares. Each of them comes with their own guarantees, with their own information gain, and with their own problems of scalability. Some benchmarks test generic performance, others test performance for specific applications like the ones we saw. And other ones are tailored to look at specific quantum gates. And some of them are natural for some hardware, but not for others. And some of them are, and it goes somehow both ways. So the idea is really, when you want to benchmark your quantum hardware, you really need to understand the main sources of noise in this hardware and what's a fair way to assess them. And this is basically what I wanted to present today. And thank you very much for listening.
Okay, thank you very much, Dr. Mezher. Let me just ask the audiences if they have any further questions. Oh yes, there is one. Can you check the chatting room?
Could you explain why use PQF? Oh, sorry. Yes. Yes. So okay. So we use the PQF for NISC because it's a scalable benchmark, and in specifically we use it for photonic NISC because it's tailored for the natural errors which happen there. So that's why, basically. So it's a benchmark which assesses the quality of the types of noise which are present in the photonic hardware, which comes with guarantees and which is scalable. No problem. Yes, there is. So I can share with you with Jean. Maybe I can give it to Jean and he can circulate. So the paper on the PQF. Yes, there is a published one. So there's a version of it on the archive, and now we're working on actually getting it published in a physics journal. In volume, it's published in PRA basically. So I can send these references when we're done.
예, 추가 질문 없으신가요? 네, 추가 질문 없으시면은 오늘 강의는 여기서 마칠까 하고요. There's one. Thank you for your presentation.
Yes, some of them are. Yeah. So some of the, like for example, quantum volume, yes, like it's a very standard benchmark and a lot of people are using it. And the interesting thing about Metric is that it's a very comprehensive list of benchmarks. So I think most of them which are being tested, so most of the testable ones are there, basically. What's the link to the Google Forms?
No, that's for the survey for the two audiences, so you don't have to consider.
Oh, okay.
Okay,
Yes.
thank you, John.
Thanks a lot, Rawad, for your talk.
Thank you.